Today we want to be able to describe how electrons flow in a wire. So just as a brief review on potential difference, remember that potential difference is analogous to gravitational fields. So when you lift something above a height, and that change in height, you will get a potential energy because it's energy that's stored. It can be turned into energy of motion, kinetic energy. So for example, what is the work per mass if we had two different scenarios, one where the ball was 1 kilogram and it moved so that it got 100 joules of energy, or we had a second ball and it stored 500 joules. What would that be per mass? So if we worked it out so that we had the 1 kilogram ball, the work per mass would be 100 joules per kilogram. For the 5 kilogram ball, it would be 500 joules per 5 kilograms, or 100 joules per kilogram. So for the mass, it would be the same. It gives it, lifting it against that gravitational field, it gives it the same ratio of potential energy. And the amount that it falls will give the difference in potential energy. So in an electric field, it's the same kind of thing. If you remember, if you have a positive charge, lifting it up against the electric field takes work. So it gives it a potential energy because that stored energy can be transferred into energy of motion, and that stored energy is called potential difference, and it's in voltage. So these are just some reminders. Instead of work per mass, we're going to use work per charge. That's the equation for potential difference. And in terms of coulombs, a voltage is equal to a joule per coulomb. That's the unit. And for electrons, it's a joule per electron, so EV. So you can show an electron volt, that's EV, electron volt, as 1 joule per electron, but it's expressed in terms of coulombs. So 1 joule per 1.6 times 10 to the negative 19th coulombs. And in coulombs, if you had a voltage, it's equal to 1 joule per electron, and you can transform that into 1 joule per 1.6 times 10 to the negative 19th coulombs. Okay, so if you have a potential difference, a volt is more formally known as potential difference, and it measures how much work it takes to lift a charge. The unit is a V for volts, the symbol is V, and it's kind of like how you pull back a spring and it has that stored energy, and then when you let it go, that energy can transform into a different type of energy. So how much work does it actually take to charge a battery? For 1 coulomb of charge, the voltage is equal to work per coulomb, and work is equal to a potential difference times charge. And so you have 12 volts times 1 coulomb, so you get 12 joules of work to charge a battery. So if you want to have it in terms of an electron instead, you can use voltage is equal to work per charge, same thing, and you go through and it's still 12 volts, but this time it's times 1 electron, and it's 12 electron volts of work to charge a battery. So they're just different types of units. So now we're going to talk about different types of currents. In this class, we're going to mostly talk about direct current, DC, which is a continuous flow of electrons. And you can think of it like a hose of water, and it's continuously flowing through that hose. And the electrons only flow one way, and it's usually supplied by a battery, and the potential difference stays constant. So the other type of current is AC, or alternating current, and it flows one way and then reverses. The potential difference goes up and down from positive 12 to negative 12, and it does this 60 times a second. So we've talked about current a little bit in this video already. Current is actually the amount of electrons that flow in a certain amount of time. In a wire, we know that electrons are the only things that move, but in a wire, they flow and they create a current, the movement of electrons. The symbol is I, and it is an amp, which is the unit, and it's charge per time, changing Q over T. So 1 amp is equal to 1 coulomb per second, which is actually quite a lot. So here's an example. It says a charge of 30 coulombs passes through a 24 ohm resistor. We haven't talked about this yet, but the unit is capital R, and the symbol is an ohm. It's a Greek letter. And this happens in 6 seconds. So what's the current through the resistor? Should be a question mark. So the current is going to be Q divided by T, the change in Q over T. So that's 30 coulombs divided by 6 seconds, and that's equal to 5 amps. All right, so then in order to have electrons flow, you must have a potential difference. So you have to have enough kind of pressure to push the electrons along. That's how you can think of that. And you must have a hose that is connected at both ends so that any water that flows out of the pump, so that there isn't any water that flows out of the pump. So the pump just makes it keep going around and around in a circle, which means that it's a closed circuit. An open circuit would have an opening where the wires are not connected. So this is a closed loop for a complete circuit, and the opened loop does not have a complete path, so there's a break here, and it is an open circuit. Okay, so that means that this circuit would not, this circuit, no electrons would flow. This circuit, electrons flow.